Let's begin with the Hamiltonian cycle problem. In this problem, our goal is to find a path in a graph that visits every vertex exactly once and returns to the starting point. To solve this efficiently, we use the backtracking technique, where we try possible paths step by step and backtrack whenever a path fails. This approach helps us systematically explore all valid solutions. Let us begin with an introduction to the Hamiltonian cycle. In graph theory, a Hamiltonian cycle is a special type of path that visits every vertex exactly once and then returns back to the starting vertex, forming a closed loop. The key idea here is that no vertex is repeated except the starting vertex, which appears again at the end to complete the cycle. This makes Hamiltonian cycles very important in problems that involve efficient traversal without revisiting nodes. Hamiltonian cycles can exist in both undirected and directed graphs. In an undirected graph, edges can be traversed in any direction, making it easier to form a cycle. However, in a directed graph, the direction of each edge must strictly allow movement from one vertex to the next, while still covering all vertices exactly once. As shown in the diagram, both graph types can have Hamiltonian cycles, but the conditions are more restrictive in directed graphs. Because checking all possible paths is complex, backtracking is commonly used to systematically explore valid paths and eliminate invalid ones. This concept forms the foundation for solving Hamiltonian cycle problems efficiently. Now let us clearly understand the problem we are trying to solve. We are given an undirected graph G, which consists of a set of vertices V and a set of edges E. The objective is to determine whether this graph contains a Hamiltonian cycle. In simple terms, we need to check if there exists a path that starts at a vertex, visits every other vertex exactly once, and finally returns back to the starting vertex, forming a closed loop. In the given example graph, we can see 4 vertices connected by multiple edges. The challenge here is not just to visit all vertices, but to do so without repeating any vertex, and still be able to come back to where we started. This problem becomes more complex as the number of vertices increases, which is why we use the backtracking approach. Backtracking allows us to try different paths, step back when a path fails, and continue searching until a Hamiltonian cycle is found, or all possibilities are exhausted. Now let's begin solving the Hamiltonian cycle problem using the backtracking approach. In step 1, we start by selecting a vertex as the starting point. Here, we choose vertex 1 as the starting vertex for the Hamiltonian cycle. At this moment, the path contains only one vertex, which is the starting vertex itself. So, we mark vertex 1 as visited, while all other vertices remain unvisited. You can see that vertex 1 is highlighted, indicating that it is added to the path. The remaining vertices, 2, 3, and 4, are still available to be explored. The visited path array is initialized as 1, minus 1, minus 1, minus 1, where 1 represents the starting vertex, and minus 1 indicates that the other positions in the path are yet to be filled. From this point onward, the algorithm will try to extend the path by choosing adjacent unvisited vertices, while ensuring that each vertex is visited exactly once. This marks the starting step of constructing a Hamiltonian cycle using backtracking. Now we are at step 2. We have already visited vertex 1. From vertex 1, there are 3 direct connections. Vertex 1 is directly connected to vertex 2, vertex 3, and vertex 4. Now we check these vertices one by one. Vertex 2 is adjacent to vertex 1, and it has not been visited yet. So, vertex 2 is a valid choice. Therefore, we move from vertex 1 to vertex 2. Now, vertex 2 becomes the current vertex. The visited path is updated as 1, 2, -1, -1. Here, -1 means the remaining vertices are not visited yet. Now we are at step 3. So far, the visited path is 1, 2, -1, -1. We are currently at vertex 2. From vertex 2, we check all its directly connected vertices. Vertex 2 is connected to vertex 1, vertex 3, and vertex 4. Vertex 1 is already visited, so we cannot choose it again. Now we check vertex 3 and vertex 4. Vertex 3 and vertex 4 are both directly connected to vertex 2. Since vertex 3 is not visited yet, we choose vertex 3. So, we add vertex 3 to the path. Now, vertex 3 becomes the current vertex. The visited path is updated as 1, 2, 3, -1. In step 4, we check the next vertex connected to vertex 3. Vertex 4 is adjacent to vertex 3 and has not been visited earlier in the path. So, vertex 4 is a safe choice and is added to the path. Now, the visited path becomes 1, 2, 3, 4. At this stage, all vertices are included exactly once. And we are ready to check whether the last vertex connects back to the starting vertex. To complete the Hamiltonian cycle. Now we reach the final step. The visited path is 1, 2, 3, 4. All vertices are visited exactly once. Now, we check whether the last vertex, vertex 4, is directly connected to the starting vertex, vertex 1. From the graph, we can see that vertex 4 is connected to vertex 1. So, we add an edge from vertex 4 to vertex 1. Now the complete cycle is 1, 2, 3, 4, 1. This forms a Hamiltonian cycle. The state space tree starts with the root node containing vertex 1, which shows that the Hamiltonian cycle begins from vertex 1. From this root, the tree branches into 3 paths, 1, 2, 1, 3, and 1, 4, representing all possible next choices. First, along the path 1, 2, the remaining vertices 3 and 4 are tried one by one. Adding vertex 3 gives the path 1, 2, 3, 4, which forms a valid Hamiltonian cycle since vertex 4 is connected back to vertex 1. Similarly, adding vertex 4 first gives the path 1, 2, 4, 3, which also forms a valid cycle. Next, from the branch 1, 3, the choices are vertices 2 and 4, and both paths 1, 3, 2, 4 and 1, 3, 4, to lead to valid Hamiltonian cycles because the last vertex connects back to vertex 1. Finally, from the branch 1, 4, choosing vertices 2 and 3 gives the paths 1, 4, 2, 3 and 1, 4, 3, 2, and both form valid Hamiltonian cycles. Thus, the state space tree explores all possible paths, and each green node represents a valid Hamiltonian cycle. Now let us look at the applications of the Hamiltonian cycle. First, robot path planning. A robot must visit every location exactly once and return to the starting point. Second, circuit and PCB design. All components are connected efficiently without repeating paths. Third, scheduling and task ordering. Each task is performed once in a fixed cyclic order. Next, tour planning and logistics. A route is planned to visit all places once and return to the start. Finally, the traveling salesman problem. A salesman visits every city exactly once and comes back to the starting city.